Okay, so this is question number 3 of the paper. So this paper is June 2012 and the variant is 4.1 and the question is 3 and the topic is again work energy and power. So let's solve this. In this question we won't need to draw any diagram because they've already given us one diagram in the question, so let's go ahead and solve it. So as you can see that the question says that a load of mass 160 kg is being pulled vertically upwards from rest at a fixed point O on the ground using a winding drum. So there's this mass of 160 kg, okay, and it was pulled vertically upwards from rest. So initially it was at this point O, and then using a winding drum it was pulled upward from point O to point A, and initially it was rest and then it moved upwards. Okay, and we know that this point A is at a height of 20 meters from the fixed point O, and as the mass is being pulled upwards towards point A, the speed with which it is moving is 1.25 meters per second. And the question also says that the load passes through a point A 20 meters above O with a speed of 1.25 meters per second. See diagram. And for the motion from O to A, which is O to A, this part, we have to find the gain in potential energy of the load and the gain in the kinetic energy of the load. So let's do part 1 first. So the first part is So for the first part, we have to find the gain in potential energy. So we know that the formula for potential energy is equals to mgh where m represents the mass and h represents the height, and g is 10 meters per second squared. This is the general formula. We can also write this as m, g, and the difference in height, h2 minus h1, since it says gain, so we're gonna take two values for height and then we're going to calculate for that. So we know that the mass is 160 kg, so we're gonna plug in the value of mass 160 and the value for g is 10, and our final height was 20 and our initial height at the fixed point O was 0, so this is the equation that we get. So we get 160 into 10 into 20, and the answer for this is 32000, or you can write this as 3.2 into 10 raised to the power 4 joules. So we're done with part 1. Our part 1 is done. Now let's move on to part 2. Which is okay, the gain in kinetic energy, we know that the formula is half mv square, and we can write this as half m v square minus u square, where m represents mass, v represents the final speed, and u the initial speed. So let's plug in the values. Half, our mass is 160, and our final speed, once our mass reaches point A, is 1.25 square, and at the fixed point O it was at rest, so the speed is going to be 0, so it's going to be this. And our final answer is going to be 125 joule. So our gain in potential energy was 3.2 into 10 raised to the power 4 joules, and our gain in kinetic energy was 125 joules. So we're done with part 2 as well. Now let's move on to part 3. Okay. So in part 3, they say that the power output of the winding drum is constant while the load is in motion, and given that the work done against the resistance to motion from O to A is 20 kilojoules, like in this path from O to A, the resistance to motion, okay, the work done against resistance is 20 kilojoules, and the time which is taken for the load to travel from O to A is 41.7 seconds. We are to find the power output of the winding drum. So for this particular thing, this part 3, we need to know 2 things. First, we need to know that what is power? Power is work done or energy or you can say that the change in energy or change in work divided by time taken is equals to power. So we know this, and they've given us the time in the question as 41.7 seconds, so we know that. Another thing is that we need to find the work which is done by the driving force, and the second equation that we're going to get is work which is done by our driving force is equals to del KE, which means that change in kinetic energy plus change in potential energy. So KE is kinetic energy, PE is potential energy, plus the work which is done against resistance. Okay, so the work which is done by the driving force is equals to change in kinetic energy plus change in potential energy plus the work done against resistance. So this is our equation, and we're just going to plug in values now. So we already did this in previous parts, that the gain in potential energy or the change in potential energy, it was 32000 plus, we know that for kinetic energy it was 125, so 125. And they say in the question, if we go back to look at the question, they say in the question that the work done against the resistance is 20 kilojoules. So we're gonna go and plug that value of 20 kilojoules as well. 20 kilojoules. Now they say that it's 20 kilojoules, which means 20, and kilo represents 10 raised to the power 3, so it's going to be 20 it's basically gonna be this thing over here. So we put all these values and we put these values into the calculator and we get 5212 joules. Okay, and now we're gonna insert this into our equation of power is equals to work divided by time. So our work was 52125 and we divide this by the time, which is given in the question as 41.7, and our final answer is 1250 watts. So this is our final answer for part 3.